This conference will now be recorded.
Hello students, very good evening to all. Today in this PYQ discussion session, I have chosen a topic which is very important, and sometimes students gets afraid of this topic as well. As I said, in the first few sessions we had discussed few numerical problems from ray optics part, also fluid mechanics part, like where the surface tension, viscosity, and the Bernoulli's theorem, equation of continuity, those things are there. So both the static and dynamic part is also important, and sometimes students used to be afraid of this particular part. So today onwards, I'll take few classes on this particular topic where I'll be gathering various numerical problems on this topic from different question papers like JEE Mains, NEET, AIMS, etc. So let us start our discussions for today. So today mostly I have picked up the questions on this particular topic from JEE Mains 2022 paper. So this question says, first question says, a drop of liquid of density, this is rho. Rho is floating half immersed in a liquid of density sigma and surface tension 7.5 into 10 to the power minus 4 Newton per centimeter. The radius of drop in centimeter will be, where you have been given an instruction that you should use G as 10 into 10 to the power, 10 meter per second square. Okay. So look, the situation I'll try to demonstrate once again from a simple diagram. Suppose this is the liquid and there is a drop of some other liquid. Okay, sometime you may see the condensed fog, they will be floating, or maybe some other liquid. So, and liquid drop ideally taken as spherical in shape. Okay, so a liquid drop is half immersed. You see, this is immersed under the water, sorry, this liquid under this liquid. Okay, so this is a liquid drop, typically spherical one, and see half of the drop is immersed in this liquid having density sigma, and this liquid drop has density rho. Okay, now you have to find out what is the radius of the drop if the surface tension is given as this one. Okay, 7.5 into 10 to the power minus 4 Newton per centimeter. Okay, so this is very simple if you understand the concept. So what is the concept here? What are the forces acting over here on this liquid drop? Here you have to somewhat recollect the principle of floating. So in this case, see, in simple case, principle of floating, if there is no surface tension, if we neglect the surface tension, in that case, what is the law of floating? We see buoyant force, okay, buoyant force and the weight, okay, buoyant force and the weight. So here, see, buoyant force will be acting in the upward direction, weight will be acting in the downward direction. In normal case also same thing happens, but in this case there is a surface tension as well. So surface tension will actually also act here in the upward direction. So I can say this is surface tension T and this is FB. So at equilibrium, see, it is floating half image. That means this is an equilibrium situation. So at this situation I can say FB, that is the buoyant force on the liquid drop offered by the liquid of density sigma, and this is the surface tension offered by the surface of water, liquid surface, and these two will actually balance the weight of the whole liquid. Okay, now the time has come to find out what is this FB, buoyant force, and what is this surface tension. Surface tension anyway is given. So what is buoyant force? Buoyant force, we know, that is the weight of the displaced liquid by this liquid drop. So I need to find out the volume. So this is the volume, half the volume of this spherical liquid. If I say the radius of this is small r, then I can take this as, say, 2 by 3, 4 by 3, 4 by 3 into half. So hemisphere I am taking. So 2 by 3 pi r cube this is the volume of this immersed part. This much is the liquid displaced by this liquid drop into sigma into g. So this is the buoyant force. Surface tension is given. And what about this mass m of the liquid drop? The liquid drop has got mass 4 by 3 pi r cube sigma into g, sorry, rho into g. This is the weight of the liquid drop. Okay, now from this we can write down FB plus T, right? So we know FB plus T, surface tension, is equal to mg. Excuse me. So FB is 2 by 3 pi r cube sigma g, and this I'll take in the left hand side, 4 by 3 pi r cube rho g, and this is equal to surface tension. Okay, surface tension here, let me first write just by T. Okay, now I have to find out what is this r. So let us take this r cube common. Okay, r cube common, and then what we get? We get 2 by 3 pi minus 4 by 3 pi. Okay, this, and see g will be common, and on the right hand side it is 7.5 into 10 to the power minus 4. This one. So I have to write r. See, there are options given here in terms of rho and sigma. Okay, rho and sigma itself. So g I have to put the value of g, pi, etc. We'll put the values, and then let me say, then let do a little bit of simplification here. See, I get 2 by 3. This is 4 by 3. So it is actually, I don't know how minus is coming. Here, this surface tension, actually we have to write surface tension per, see, surface tension per unit centimeter it is given. I have to actually say this surface tension will act all the way, okay, from here like this, like this. This is the hemispherical one. So along this perimeter, okay, like this it will act in the upward direction. So I have to multiply 2 pi and small r over here. 2 pi and small r I have to multiply over there. Okay, so that is also there. Okay, so there are a few more things over here. Let me just incorporate. Oh, yeah. So let me write 2 pi small r over here. Okay. So from here, then what we get? Okay, I see here I have rho and sigma. This is sigma and this is rho. Okay, one sigma will be here and one rho will be here. And in this case, see, yes, let me just do a little bit of simplification over here. So what we get here is, okay, so this 4 by 3 by 2. Okay, so it will be, so this is actually becoming 2 sigma. If I take this, okay, let me take 4 by 4 pi by 3. Let me take this common. Then what I get, so I have to multiply divide. Okay, so this is will be sigma by 2 and this is rho into g over here. Okay, so this is actually equal to 10 to the power minus 4 into 2 pi small r. So here you look, this pi I can cancel out. Okay, so this rho, see this 4 can cancel. Okay, then it will be 2 over here and 3 in the up. Okay, so in the numerator. So what we get from here, I see. So actually this will be plus and this will be minus. Okay, so here the minus and here plus this. Okay, this is the thing. All right, so now see from here it is r square 2 rho minus sigma into, okay, so 2 will be multiplied here again, so this will be 7.5 into 10 to the power minus 4. This I have striked out from both sides, this also will go away. Okay, so only 3 will be multiplied over here. Okay, 3 will be multiplied, and what else? Okay, down there will be 10. Okay, so then what is r? R will be square root of 7.5 into 3 into 10 to the power minus 4 divided by 2 rho minus sigma into 10. Okay, and see this was in centimeter, then per meter if I make, this will be 10 to the power minus 2 alone. Okay, if I make this as the meter. Okay, so see 1 meter, see 1 meter is equal to 100 centimeter, right? So from there I can actually write this as meter square, sorry, meter per meter. Okay, so with this simplification, look further if we do it, okay, so from here you'll be easily able to get 15 by 2 rho minus sigma. So in between I have jump one step, you can just do it later on. So this will be in centimeter. Okay, 15 by square root of 2 rho minus sigma. Okay, so dear students, I think I took a long time to do the calculation properly. You can do it quickly in your notebook. Okay, but the main concept is here that the buoyancy force or the buoyant force and the surface tension, that will balance the weight. Surface tension will act actually all the way this like this. Okay, if you have this liquid in a hemispherical shape, liquid drop in a hemispherical shape, say it will hold up, surface tension will hold up all the way through this perimeter. Okay, like this. Okay, and we know surface tension actually force per unit length. Okay, unit length, that is surface tension. Okay, so that's why here we had to multiply 2 pi r with the total surface tension. Okay, here the surface tension per centimeter is given. So what is the surface tension? Here we are getting, that is actually the surface tension given 10 to the power minus 4 and 2 pi small r. You can keep this in centimeter. Okay, then this will be Newton. If this is centimeter, then it will be Newton. Okay, so that you can go. like go for the calculation and do the right thing here. Okay, so here the option first will be the correct answer for this question. Okay. Okay, let us go to the next problem. So this problem is also from JEE Mains 2022. The question says a water drop of radius 1 centimeter is broken into 729 equal drops. Okay, if the surface tension of the water is given like this, 9 per centimeter, then the gain in the surface energy up to first decimal will be. Okay, what is the question? Question is what is the gain in surface energy? Okay, so look here, what the question saying is this. This is a liquid drop. A water drop of radius 1 centimeter is broken into 729 equal droplets. So this is what the question says, that this has suppose a radius capital R. Okay, and that is 1 centimeter given over here, and this is broken into tiny parts, equal drops. Okay, and how many of these are there? This many equal drops. Let me take radius of 1 is this. Okay, so what is the gain in the surface energy up to the first decimal? Gain in means, so surface energy is actually surface tension into the change in area or increase in area, change in area, surface area. So this is actually gain in energy. Okay, so in this case surface area will increase if you break a drop into multiple number of droplets, then the change in area will be positive. That means the area of surface area, total surface area will be increasing, whereas the total volume remains the same. That means what? That means 4 by 3 pi capital R cube is equal to the 729 4 by 3 pi small r cube. Okay, but we don't know what is the small r cube. We have to find out that. Okay, from this relation, so 4 by 3 pi cancels each other, right? And this is 1 centimeter, right? This is 1 centimeter. So what will be the radius of each of these small droplets? Okay, so this is the radius. Okay, you can try out how to get this value. So you can try out to get this value. See, 9, 9 and 9. How much you get? 81 into 9. So this will give you, right? So this will give you 9, r by 9, and this is 1 centimeter. So in centimeter, if you want to find out the surface energy, this is given in dyne per centimeter. Let me keep this as centimeter. So r will be 1 over 9 centimeter. So the students, see, I have got the radius of each of these smaller droplets. Now I have to find out what is the gain in area. Okay, gain in the area. So in this case, previous case, the area would be, okay, let me find out the gain in area. That means final area final, that is 729 into 4 pi small r square. Okay, and initially the area was 4 pi r square, capital R square. Capital R is 1 centimeter. So in this case, see, final area, what we get? Okay, let this 4 pi be there. So this will be 729 into 4 pi divided by 81. So this will be 9. That means, you know what we get? 36 pi. Okay, and what we get here is 4 pi alone. Okay, this is centimeter square actually. Okay, so what is the gain in area? Gain in area or change in area here is actually 32 pi centimeter square. Now surface tension, see what is the surface energy, change in surface energy. Let me write that as delta U. So this will be 32 pi into 75 dyne per centimeter. Dyne per centimeter. See, this is centimeter square, this is, and this is dyne per centimeter. Okay, this will give you a value to 75 into 32 into this pi. Let me take this as 3.14. Okay, this is dyne into centimeter cube. Okay, and this value is a really big value, like this. Okay, this is dyne centimeter cube. Now let me tell you about the options given over here. The options are given over here are like this. What are the options? Options are, option A is 8.5 into 10 to the power minus 4 joule. option B, it is 8.2 into 10 to the power minus 4 joule. C, 7.5 approximately into 10 to the power up to first decimal, it is said, minus 4 joule. 5.3 into 10 to the power minus 4 joule. Okay, actually we can do little bit of see dyne I can write in terms of Newton, and this I can write in terms of meter. Okay, so see this is okay, dyne in 10, see 1 Newton means that is what 10 to the power 5. Okay, so 10 to the power minus 5 then. Actually dyne I have to write in 10 to the power minus 5, that is fine. I just want to make it into Newton. Okay, because in the joule unit I have to bring, that is actually Newton into meter, right? Newton into meter. Centimeters, okay, 9 per centimeter, it is actually centimeter. I'm sorry, yeah, centimeter. So this will be 10 to the power minus 2 again. Okay, so you look here what we get, 10 to the power minus 7. So I have to go up to this first decimal like this and see, then I get 10 to the power minus 4. This is joule, actually this is Newton into meter. Okay, so this is how we have to do this problem, and we have these options here. Okay, so option C will be the correct answer for this question. Okay, let us go to the next problem. Okay, so terminal velocity Vt of a spherical raindrop depends on radius. Okay, how it depends on radius for the spherical raindrop. See, any raindrop when falls, there will be mg downward, Fb binds force or bind force, and also viscosity, that is Fv, let us say. So they will actually cancel, like balance each other, then the speed of this will be the terminal velocity. Okay, so if suppose the terminal velocity is becoming such that Vt, then I can write this Fv. Okay, let me write Fb. Fb will be anyway this volume, so radius suppose smaller, so volume of this spherical raindrop, and then density of itself. Okay, sorry, this is density of the air suppose, or the this atmosphere. Okay, into G, okay, into G. And what will be this M? M will be 4 by 3 pi r cube rho G, where rho is the density of this liquid drop, rain drop. And FV, since the velocity is Vt, then it will be 6 pi eta r and v. Okay, so look from here, I have to actually find out what is the variation of r with the terminal velocity. So terminal velocity, here the formula is actually here, the equation of motion is this is equal to mg. This is my equation of motion. So let me put these values and see if v I have to keep. So 6 pi eta r and b, let me skip, like keep in this side, and this will be 4 by 3 pi r cube into g rho minus sigma. Okay, all right, so this r will cancel each other here, no, not cancel, this is actually, this is making r square over here. So what I'll have here, vt terminal velocity is equal to this pi cancel each other, and this 6 eta will come in the denominator. So this will be actually 2 by 9 eta g rho minus sigma into r square. That means it is varying as r square. Okay, vt is varying as r square. So this is the answer, option C. All right, so this actually you should be thorough with this formula and all, so that you can just see and just within 30 seconds, not even 30 seconds, within 15 seconds you can actually answer this question just by seeing. Okay, now let us go to the next problem. Okay, so this problem is very interesting problem. Okay, so the question says two cylindrical vessels of equal cross-sectional area 16 centimeters square contain water up to the heights 10 centimeter and 150 centimeter respectively. Vessels are interconnected so that the water level in them become equal. The work done by the force of gravity during this process is how much out of this? See, let me give you a representative diagram over here. Okay, so let me just draw. This is having same. Okay, so let us have connecting rod, like connecting pipe over here. Let's take almost identical cross-sectional area. Maybe this is okay. So initially, suppose this was closed. Okay, and see, one has liquid up to 150 centimeter. 150 centimeter. Let me just write this as H1, say, which is 150 centimeter. Here H1 is 150 centimeter. H2, it is little less, that is 100, right? This is 100. centimeter. When this lock is open, they will be interconnected, and what they will try to do, they will actually try to do this. They will get same height of the liquid. This is from the very property of liquid. Okay, and this height, let it be some h height. So what will be the height actually? Say if this is h1 and this is 100 centimeter, h2, let us say h2 for the time being. So the height, equal height will be actually h1 plus h2, the average of that. Okay, that means this is 100 plus 150. h1 is 150. Order is okay. Let me write in order. 150 plus 100 divided by 2. That means 250, right? 250 by 2. This will be 155 actually. Okay, sorry, 125. This is in centimeter. This is the height we get, isn't it? 125 we get after opening the valve. Now the question is, how much is the work done? Work done in the sense we can get the difference in energy. Okay, work energy theorem, right? So difference in the potential, gravitational potential energy will be equal to the work done by the gravity. Okay, I hope you agree with this. So what is the gravitational potential energy difference? We know in first case it is, suppose the volume, sorry, the amount of water we have, the mass of the water or liquid here in the first vessel is m1. So m1 h1g, right, plus the potential energy, this is the initial potential energy, okay, m2 mass of this into g into h2 mgh, okay, and final one will be final one, this is water only, okay, water only. So final one will have the same density, same height, they will have the same mass, right, same process and same volume and same density will have the same mass. So 2 mg into the height, okay, this much I can say. Now you take the difference uf minus ui, so that will actually give you the work done. Okay, obviously we have to take the modulus. Let me check now. So what is the initial potential energy? So density of the water is given, volume we know, centimeter square area, and this is given. Okay, so let me write m1, that means area of cross section, h1 into rho into g, okay, into further h1. Okay, this is m h plus a h2 rho g into h2. Okay, so this was the value. This is mg AMG weight into this is the height. Okay, so this is how this one also. Okay, so I can actually write, see what I write. I can write A rho G common. I get H1 square plus H2 square, right? The final answer will write later. Let me write this. I can write actually this is 2mgh 2 into m is a rho g anyway, okay, into 1 h will come here. This is m g and h, another h will come. Okay, okay, so this g will not be there. So I get 2a rho g, this is h square. Okay, so what is the difference in energy? That is uf minus ui. Let me find out that. So 2, let it be there. So this is a rho z common. This is 2h square, and this will be minus h1 square minus h2 square, right? 150 square, and this is 100 square. I mean, I can take this positive. Okay, so this is the difference. What is this 2h actually? Okay, we have to take the mod of that. A rho g, let it be 2. This h1 is actually h1 plus h2 whole square. Okay, I think I can go with this also directly. I can put the values. Okay, so h1 square plus h1, so 150 square plus 100 square. Okay, so this will be 200. Okay, so this is 225 plus this will be, so this is a big number, 32500. Okay, yeah, so this is the number, and this number is actually 125 whole square. Okay, 125 whole square we have to get. So this is into 2. Okay, into 2. This will give you actually, obviously this will be, there will be loss of energy, only loss of energy. Okay, so mod I have to take. So this is 131,250, and this is actually 32500. Okay, so this will be in centimeter square. Okay, this is centimeter square, and here centimeter square will be there. Okay, so yeah, actually we have to see the options were joule. Okay, we're right in terms of Newton in meter. So this is 10 to the power minus 4. Let us multiply from the beginning. Okay, and this a is actually 16 centimeter square. 16 centimeter square into 10 to the power minus 4. Okay, this is in meter. Density 1000. Okay, and G10 along with this value, obviously there will be minus sign over here, so I'm taking the modulus of that. This will come here as 1250, and here this 10 to the power minus 4 is there. Okay, so how much will be in Newton into meter? Okay, so I think in between somewhere I have missed some point. Anyway, this answer will be 1 joule. Okay, this answer will be 1 joule, no doubt about it. Okay, so calculation can be done correctly. I'm not repeating the calculation. You just cross check and then see whether you are getting the same thing. Okay, 1 joule. Okay, so this is another one. So this question says an ideal fluid of density 800 kg per meter cube flows smoothly through a bent pipe, okay, as shown in the figure, that tapers in cross-sectional area from A to A by 2. I'll just draw the figure for you here. I have forgotten to give the figure. So what is the figure over here? Okay, let me read the question once again. An ideal fluid of density 800 kg per meter cube flows smoothly through a bent pipe as shown in the figure. Let me give you the figure over here. Bent pipe. Kind of this. Okay, so this is the bent pipe. Look, the cross-sectional area over here is A and this is A by 2. Okay, A by 2 over here. And see the height from here, it is given as 1 meter. Okay, so this is 1 meter height. What else is given? The velocity here is v1 and here the velocity is v2, given like this. Okay, coming out of this, as you know. Okay, the question is saying that the pressure difference between the wide and narrow sections of pipe is given. Okay, pressure difference is given. The wider section, at the wider section, the velocity of the fluid is this much. And what is the value of x then? This is actually very simple question. So what you have to do here, you know, right? What you have to do. So the density is given, that is very fine. So first of all, we have to find out the relation between v1 and v2. Okay, so equation of continuity. First we have to use equation of continuity. Equation of continuity. So what is that? That is a v is constant. That means a1 is a, v1 is equal to a2 is a by 2, v2. Okay, So from here, I'll get a relation between V1 and V2. Look, this A cancel each other. So what we get? I get V2 is equal to 2V1. This relation I get. Now what I have to do, I can use Bernoulli's equation. Okay, Bernoulli's equation for a dynamic flow. Okay, so what is that? The pressure energy plus gravitational energy plus the kinetic energy head. So this is gravitational potential head, this is pressure energy head, pressure energy per unit volume, gravitational energy, potential energy per unit volume, and kinetic energy per unit volume. This is actually, I'm writing the in general equation, so this is constant according to Bernoulli's theorem. Okay, so this I can just write for this end and this end, that should be the same. Let me write it here. So what I get for the wider end, P1 say pressure, and rho GH1 the potential energy head, and kinetic energy head, let me say half rho V1 square. Similarly, in the lower end or the narrow end, P2 plus H rho and 0, right? Height is 0 there, isn't it? So this is 0 plus kinetic energy head, we know the velocity is V2, right? Half rho V2 square. Now what I have to find out? I have to find out the velocity V1. So that is what is asked in the question. What are section? What is the velocity of the fluid? So let me see this thing. P1 minus P2. So this is actually given. Okay, that I can write. And see, this is rho GH1. This is there, and here I can write half rho V1 square minus V2 square. Okay, so what is V2? V2 is 2V1. Let me write in terms of V1. Then I get V1 minus 2V1 whole square. So in this side, then I can write V1 square is equal to 2 whole into this 2 by rho. This is P1 minus P2, that is given the pressure difference 800 kg per meter cube. 800 kg per meter cube. Okay, plus rho, the density, the fluid is not given anyway. Pressure difference is given. So let me cross check if we can somehow escape from the rho. I see the density of the fluid is 800. I'm sorry. So that is given 800. Okay, I'm sorry. This is 800. Okay, let me just clean it. So density is given. I can put the values later. So here, what is that pressure difference? 4100. So pressure difference is that. So V1 square from here, okay, then I get 2 by rho whole into P1 minus P2. This I can write as this, plus rho is 8,000 per meter cube, sorry, 800 per meter cube, kg meter cube, okay, kg per meter cube. That is that density H. Okay, G is actually 10 meter per second square, okay, and this is H. H is given as 1 meter. So 1 meter, then what I get the unit? See, this is kg, okay, kg. This is meter, meter, meter square. So this will be kg per meter, kg per meter per centimeter second square, okay, meter per second. Okay, we know pressure will be actually force by area. That means, in terms of unit, this is m into g. If I write mg, so this is kg meter per second square, kg meter per second square, kg per meter, okay, this is kg meter per second, okay, kg meter per second square, this, and this is actually meter square. So 1 meter will be down, this is, okay, so meter is, okay, meter per second, this is kg, okay, so I have here kg. I'm just taking the unit kg per meter second square. So this is in SI unit. This is all right. So this will have the pressure, unit of pressure itself. Okay, so this could be added. Okay, so this is 2 by 800. Okay, so look then what I get, 8,000 over here. Then 2 by, okay, let me write this as 400, 1 over this, and this is, sorry. So I have to make it in terms of root x by 6, right? Root x by 6. So this value is happening how much? This is like this, right? Yes. So this is, see, I just type this out. So I have to make 6 over here, okay? If I have to make 6 here, then I have to multiply 3 by 2. So look, if I multiply 1 into 3 by 2, here 4 into 3 by 2. Okay, so this will make this as 6. Okay, this will be 6, and I will have here 3. Did I do any mistake over here? Up row is fine. 400 goes. Okay, let me just go up to the final point, and there I'll think. I have got already the 6 in the denominator. Let me write that. So this will be 6, right? So this will be 1 to 1 into 3 by 2 into 6. Okay. So this will give you 3. This one. Okay, 363 by 2. I don't know. Somehow I'm getting this 2. Oh, yes. I've done a serious mistake in the calculation. Let me cancel this part and see the mistake I have done. Please don't do this while attending this question in the exam. See, I have done this serious mistake over here. So this was b1 square, this was b2 square. I have written b1 minus b2 whole square. So that is the mistake I had done. So let me correct it here. b1 square minus b2 square. So okay, so here v2 was actually v2 to v1. Okay, so there is again a minus problem. Okay, anyway, I'm just taking for the sake of positive here. Here I see. I'm sorry, today is my bad day. I'm doing a lot of mistakes in the calculation today. Somehow this is the thing. So now look here, I'll get v2 square is 4v square, right? 4v1 square, and this is v1 square itself, right? So what I get here 3 by 2 row v1 square. This is already I have got. So v1 square is equal to 2 by 3, then 3 row, and this is actually 8,000 plus 411 4100. Okay, this much is fine. This was fine, right? Isn't it? So now 2 by 3 into 800 here, and here it is. These two guys will actually suit each other. One, this is 12. Let me multiply 3 by 2. What is happening? Further, we have 2 over here, so 3 by 2 fine. Okay, let me write it here into 800. Okay, this is coming 12 only. Okay, so I have to make it into 6. There could be a small mistake again somewhere. I'm doing really bad today. Anyway, I'll just write it here. This by row, and this let it be 8,000 by 800. This is row, the value of row. Okay, this is 800. Okay, so this, okay, this will be 10 actually. 10 here. 2 by 3, 4 into this by 8 plus 10 here. I guess this will be okay now. So 2 by 3, this will be 121 divided by 8. Okay, further the same mistake. I see. Let me just do one thing here. 3 by 3. Okay, this would keep everything all right, isn't it? This is 4. Okay, let me see the option over here. Like the question is there any other factor over here? No. Root x by 6. Root over x by 6. Okay, yes. Okay, now things will be all right, isn't it? So it is actually 363. Here it will be 339 36. That means 4 into 9. Okay, now v1, I think earlier also things was all right. Okay, this is 363 and this will be 2 into 3. Okay, so square root of 363 divided by 6. Okay, so the value of x will be then 363. This is in, okay, meter per second. Anyway, so this is the thing. I'm really sorry, I have actually done many mistakes in the calculation in between. Okay, I'll just stop with this, the last problem for today's session. I would have done many more questions in the today's session, but problem is in between I had lot of stoppage due to the calculation mistake. Anyway, let us conclude with this problem for today. The question is saying that See the question itself. Let me give you the options over here. Do I have? Okay, let me just read the question first. If rho is the density and eta is the coefficient of viscosity of fluid which flows with the speed v in the pipe of diameter d, the correct formula for Reynolds number. So the options are given over here. Option A, what is option A saying? Option A is Re is equal to eta d by rho v. Okay. Option B says it is rho v by eta d. Option C says it is rho vd by eta, and option D says it is eta by rho vd. Okay, so which one is the correct option? So this you have to simply mark up and keep in mind. The exact relation is the C. Okay, Reynolds number for a fluid which has density d and flowing with velocity v inside a tube which has diameter d, that is the rho v d by viscosity eta. So this will be the answer. Okay, Reynolds number is actually a number. This is actually unitless quantity, unitless or dimensionless quantity, you can say. If you do the dimension analysis, then also you can find out. Okay, so suppose eta we know 6 pi eta v. Okay, so force is F is equal to 6 pi eta r and v. Okay, from here we can find out the dimension of eta. So this eta will be, then this is dimensionless rv, so eta will be F, that means ml to the power minus 2, r is l, and v is l to the power minus 1. This L will cancel each other, and see what I get. I get m l to the power minus 1 to the power minus 1 from here. Okay, so look, this will give the same dimension because Reynolds number is a number. It gives a dimensionless quantity. Let me find out from here what is rho. Rho is the density, that is the mass per unit volume, mass per unit volume. And what is this v? V is l to the power minus 1. What is d? D is again having a dimension of length. So what I get here, so this l square, so ml to the power minus 1 to the power minus 1. So these two should give the same same dimension. Obviously, again, one more thing is this one. Okay, this is also dimensionless quantity in this case, but for that case you have to remember that rho vd will be in the numerator and eta will be in the denominator. Okay, so this is how. So these two are actually dimensionless, but here you have to know that eta will be in the denominator. So that is another point. So this options are so clever actually. You can see that C and D both are dimensionless, but here you have to remember that eta will be in the denominator. Okay, so that's why this is not true, and others are obviously dimensionally not correct. Okay, so with this I'll stop it here for today. In the next class we'll take up many more problems on the fluid mechanics. Okay, so typical problems are there. Many critical problems also will be coming in this: capillary rise from surface tension, etc., and also from Bernoulli's theorem, equation of continuity, and also from U-tube, like U-tube balance problem. Okay, so those problems will be discussed in the subsequent classes from various papers, competitive exam paper. So for today we'll stop it here. Bye for today. Thank you.